All right, so now I'm going to go ahead and define Kirchhoff's current law, KCL. Let me grab my highlighter. And KCL just states that the sum of all the currents into a node is equal to 0. Okay, so in the KVL that we discussed previously, that was the first law that was very important. That's the sum of all the voltage drops in a loop is equal to 0. Kirchhoff's current law, or KCL, has to do with currents and rather than voltages, and it says that the sum of all the currents into a node is equal to 0. So what does that mean? So if I draw a node with a couple of wires coming in, again, we remember that a node is just a place where a bunch of wires meet. And let's say I have a current I1 coming in here, a current I2 coming in here, and a current I3 coming in here. Well, pretty simply put, Kirchhoff's current law states that the sum of all the currents into a node is equal to 0. Well, this is my node, and these are all three the currents in the branches that connect to this node. And so I can write my KCL expression pretty easily. I can just say that I1 plus I2 plus I3 is equal to 0. And that's it. That would be my KCL expression for this node. Every node in every circuit has a KCL expression, and the sum of all the currents into that node are always equal to 0. However, there is a different way to write this expression, different way to think about KCL, which I particularly find incredibly useful. And you can use, you can think about it this way and it'll be perfectly fine, but there is another way to think about it, and it is that the sum of all currents into a node equals the sum of all the currents out of a node. Okay? So the sum of all the currents into a node is equal to the sum of all the currents out of a node. Okay? And so if I use this expression, let's say I'm going to draw the exact same circuit, but in this case, I want to flip the way I define I3 so that it's flowing out of the node instead of in. Then I can, just from what we learned in the previous video, I can define I3 in the opposite direction, but I have to make sure that I flip the sign. Okay, so if I were to write my expression for KCL now, based on my second definition, the sum of all the currents entering the node, right, into the node, which is this, would be I1 plus I2. And it would be equal to the sum of all the currents out of the node. Well, the only current out of the node is minus I3. So I could write that I1 plus I2 is equal to minus I3. And then, of course, if I just add I3 to both sides, I end up right back where I started with I1 plus I2 plus I3 equals 0. Okay? And so just a real quick example of something that, some circuit that you may encounter where, and in the next video I will give an example, but some circuit that you may encounter, you might see something like a node here, and then I've got a couple of, I know for a fact I have a 1 milliamp flowing this way, and then I have maybe 3 milliamps flowing this way, and I'm curious, what is the current here? Well, quite easily, it's the sum of the currents out of the node. It would just be 1 milliamp plus 3 milliamps, or 4 milliamps. All right, so that was just a little brief explanation of KCL, and in the next video I'm going to go ahead and use it to solve a circuit.